Now we're going to think about another parameter. We're going to think about a single mean. And again, if we had done a little bit more probability, I could show you the proof for why the standard error is calculated the way that it is. And I'll put the video where I do that proof in the description here. But essentially, you're just going to believe me that the standard error for a single mean is sigma over the square root of n. So again, I'm going to be able to say that if n is large, then x bar, the sample mean, follows a normal distribution centered at mu with standard error sigma over the square root of n. And in this case, we're going to say that large means n needs to be greater than or equal to 30. So if the underlying population is symmetric, sometimes you can get away with a smaller sample size, but we rarely know anything about that underlying population. So you should just be checking this condition, the n greater than or equal to 30 condition. The other problem here is I've said that the standard error is sigma over the square root of n, but we don't know sigma. That would be the true population standard deviation, and we can't know about the population. That's why we're doing inference. So the problem is we're going to have to approximate sigma using s, the sample standard deviation. So we're going to say that the standard error is approximately equal to s over the square root of n. And the thing that's strange about this is when we approximate sigma with s, we can no longer use a normal distribution to approximate the sampling distribution. Instead, we have to use this thing called a student's t-distribution. And the t-distribution looks a lot like the normal distribution, but it has fatter tails. So I'll draw you kind of an exaggerated version of that. So if this is what the normal distribution looks like, then the t-distribution is more like, so it has fatter tails. There's more of the distribution out in the tails. And I'll show you a real graph that is better than my hand drawing. When we are defining the normal distribution, we just say it has mean mu, standard deviation sigma, and then we can characterize, the normal distribution mu, comma, sigma. The t-distribution only has one parameter, and it's not the mean or the standard deviation, it is the degrees of freedom. So this is a new idea, the degrees of freedom. I often abbreviate it as df, and we calculate the degrees of freedom based on the sample size. In this case, we're going to be doing inference about a mean, and so we're going to be doing the degrees of freedom are going to be n minus 1, but there are other degrees of freedom that we'll use when we have other parameters. And as n approaches infinity, as the sample size gets bigger, the t-distribution is going to look more and more and more like a normal distribution until it basically is a normal distribution. So here is an example. In this picture, the black line is the normal distribution. So this is normal. And then the red line is a t-distribution with df equal to 5. And the blue line is a t-distribution with df equal to 15. So the way that you can tell that it's a little bit different is, again, the thickness of the tails. So if we look out in the tail, the black distribution is getting closer to the x-axis. The t-distribution with 5 degrees of freedom is a bit higher. Even the one with 15 degrees of freedom is a little bit higher. And then the corresponding thing is happening in the middle as well. So it's a little bit lower or a little bit lower. To make up for those tails being fatter. So this is just a different theoretical distribution. It has its own name, but we specify it using the degrees of freedom. And just a moment of history, the t-distribution was discovered or invented by this man named William Seeley Gossett. And he was working for Guinness at the time, and he wanted to have a way to tell if Guinness was really consistent. So he was doing statistics basically to see that the beer had good consistency when it came out of the production line. And he came up with a bunch of statistical ideas, so that's one of the birthplaces of stats. But he decided he wanted to publish a paper about this distribution that he came up with, but he didn't know if his employer would like it that he was publishing research papers. And so he wrote the papers anonymously, and he would sign them a student, like a student of statistics. And so that is why the distribution is called the student's distribution rather than, the Gossett distribution, for example. So here's kind of the last word. Essentially, if we have a big enough n, in this case we're going to check n greater than or equal to 30, then we're going to approximate the sampling distribution for a mean using the t-distribution with n minus 1 degrees of freedom. And we're going to calculate the standard error using s over the square root of n.